Hello! Today I will talk about our recent work on Neuro-Symbolic Semantic Code Search. Today, ML approaches are prevalent in software engineering applications, including semantic code search. A common way for performing semantic code search is using embedders for programming and natural languages and measuring the similarity of the query and the code in some latent space. A lot of prior work has focused on making programming language embedders more expressive or developing new ways to define the similarity metric and the corresponding latent space. However, embedding of the query has always been delegated to powerful large language models and has not been studied in the context of semantic code search. This is what we study in this work. We propose improving the query embedding for code retrieval so that it allows us to represent the query more faithfully and thus enable precise retrieval. Additionally, the pipeline demonstrated here does not allow multi-stage reasoning on the code, which might be necessary for queries with multiple clauses or conditions. We based our approach on our intuition of how a real engineer would locate a snippet of code. For example, finding a bubble sort could require locating parts of code that look like they are handling arrays, and then checking whether the found array is being traversed, whether its elements are being compared to each other, and whether they are being swapped as a result of that comparison. Based on this intuition, we focus on identifying the entities and the actions in the query and how they relate to each other. We do that by creating the semantic parse of the query. Intuitively, entities are likely to be represented as nouns or noun phrases, whereas actions will be verbs or verbal phrases. The whole of the query is modeled with a neural module network whose layout is defined by the structure of the semantic parse. Two distinct modules, one for entities and one for actions, are jointly trained within the module network, where entities are leaves and their output is passed as input to some action module. The entity module measures semantic relevance of every code token to its input entity. The action module works in a closed fashion. It gets relevant scores and inputs for all but one entity in the query, and it tries to estimate the relevant scores for this missing entity. The assumption is that if the query corresponds to the code, the action module should be able to correctly estimate missing scores. The similarity of code and query is estimated by measuring the similarity between the prediction of the action module and masked relevant scores. Now to results. We have found that this approach is quite successful on both datasets that we used for evaluation, CodeSearch.net Python and CoSQA. Besides evaluating on the full CodeSearch.net Python dataset, we include two reduced data scenarios, only including 10 and 5,000 training examples correspondingly. In all cases, the correct code snippet is evaluated against a large number of random destructors, and the result reflects how highly the correct query code pair was ranked among all the destructor pairs. Besides main evaluation, we also performed a number of analyses to understand the performance of the NS3 model better. First, we looked into more complex and more compositional queries. The plots in the top row show how the number of arguments to the action affects the performance. We suggest that this number is a proxy for the complexity and for the level of detail in the query. The plots in the bottom row show the performance broken down by the number of nested action modules as a proxy for depth or compositionality of the query. The left column contains the results for the CodeSearch.net Python dataset, whereas the right column is for CoSQA. We further demonstrate the sensitivity to the details of our model versus the baselines. Particularly, we evaluated their performance on some query code pairs and then perturbed those queries so that the queries no longer correctly match the code. We used two types of such perturbation. In the first one, depicted in the left bar, the models are faced in a query with a noun phrase randomly replaced for another noun phrase. The rest of the query remains unchanged. In the second one, shown in the right bar, the action verb in the query is randomly replaced with another verb, while the rest of the query again remains unchanged. Models were evaluated by computing the ratio between the new prediction for the incorrect pair and their original prediction for the correct pair. In a more sensitive model, the similarity after perturbation should drop significantly, thus leading to a lower ratio. Finally, here we demonstrate the outputs of NS3 modules at different stages of training. The middle column shows the semantic relevance scores assigned by the entity module, and the rightmost column shows the corresponding estimates made by the action module. This concludes my presentation. Thanks to the audience and my wonderful collaborators.